This tutorial is going to be a little bit different than normal in that I'm not going to start in notes right away, but I'm going to try to show a little bit of animation on a PowerPoint. I want to show you how a standing wave evolves when a energy is transmitted along a medium down, let's say a slinky, hits a barrier, bounces off, and starts interfering with itself. It's difficult to show in real time, so I'm going to show it step by step, and it's very important you kind of get an idea of why the standing wave forms, and then at the end of it I will summarize key points on the first page of the note sheet. So just try to pay attention to this, and if any questions arise, don't hesitate to ask. So what you see before you under the evolution of a standing wave is, imagine we have a string that is stretched between two barriers as indicated by these vertical lines. And so what we're going to do is imagine there's something at this end that is going to jiggle the string up, down, and up. We're going to go back and forth between the two extremes of this and all the way down. Okay, so I'm going to press some arrows here. Hopefully this goes well. All right, so we're going to move our hand up and down. And if I show that here, so that's the motion all the way there and then all the way down for a half a cycle. So what we'll see if we were to take a snapshot of the medium after that half a cycle is this. And so what you want to understand is this is time zero. At time zero, this is where the medium was. And then our hand went up till we got to a peak. And then at the end of time 2, this is where we are. So it's kind of looking the opposite way we're normally used to looking at graphs, where the beginning of time is at the leading edge of the wave. So this is what our wave front looks like. It's a crest. Okay, no big deal. Now we're going to continue with our hand. We're going to move it, continue moving it down towards the bottom of this part here and then back up to complete one cycle. So while we're moving our hand that way, okay, so we complete 3 and 4. During that time, 1 and 2 are going to shift. In other words, the pulse is going to have shifted to the right in the time that it took to create 3 and 4. And so now we have a full wave, and this is how you can understand how it develops. So at the end of the full cycle, this wavelength, or this wave, the pulse, is now approaching our barrier right here. And as we showed in class, when a pulse hits a barrier, it will reflect. And in fact, not only reflect, but we saw, if we're paying attention in class, that it inverts itself. So now we're going to continue moving our hand up and down. So we're going to continue our cycle. We'll do 5 and 6. So we've got 3 and 4. Now we're going to add 5 and 6, and during that time, we're creating 5 and 6. 1, 2, 3, and 4 aren't just going to sit there. They're going to keep moving. And so what we get, there's a creation of 5 and 6. 1 and 2 invert and bounce off, and 3 and 4 move forward in time. Okay, so I might rewind that if I were you. I can't really do it here on Excel. And so what we get after 1.5 cycles, and what's important to note, is that these two waves are completely overlapping each other. So we're going to get, if we look at the superposition of those, a wave that looks like that. We have a zone right here that has a very large amplitude. It's double the amplitude of the original wave. And that's only, again, after 1.5 cycles. So again, we're going to keep moving our hand. We never stopped. All right, so now we're going to do 7 and 8. So while we're creating 7 and 8, okay, 5 and 6 are going to shift to the right. The orange part here is going to bounce off, and then the original 1 and 2 are going to keep moving to the left. So it looks like that. So we have 7 and 8 are created during that time. 1 and 2 keep moving to the left. 3 and 4 bounce off and invert, and 5 and 6 slide to the right. Again, I showed this in sequence, but during the creation of the 7 and 8 pulse, all those things happen at the same time. And now, again, you notice after 2 cycles, something very interesting happens. At right here and here, those are completely overlapped in phase, so we're going to get maximum constructive interference. If you notice right here in the middle, there is no amplitude at all, nor are there at the ends. So if I put this all together, okay, I get a wave that looks like this. So there is what is called a node here. The N stand for node. We'll summarize that in the notes. Okay, those are areas of destructive interference. And then where they are constructively interfering here and here are called antinodes, AN. So those are terms that are very, very important. So if we continue on our cycle a little bit more, after 2 1/4 cycles, this is what I've drawn, so I didn't go through the evolution, but 9 would be another quarter cycle, so we create this part right there. If I look at the superposition of all those, and if I add this amplitude and this amplitude, I get 0. If I add the amplitudes here and here, 0. If I add this amplitude and this amplitude, I get 0. And if I continue along that, I see at one given time, exactly at 2 1/4 cycles later, I have absolutely no energy in the system. And so the slinky, the rope, will look like that. And that's very different than a traveling wave. If I'm just creating waves by moving my hand back and forth, at some point anywhere along this rope, I'm going to see a squiggle that looks like this. That's a traveling wave. Okay? And then the next instant, that traveling wave is gone, and it looks like this. But in a standing wave, because of the interference effects of the reflected waves and the incoming waves, I can get at one point, there's absolutely no energy in the system. And that's unusual. So we will flesh this out more when we do examples in that, but that's the key to a standing wave. So let's summarize what makes a standing wave on our note sheet here. Okay, so let me just maximize this. Okay, so standing waves are a special case of resonance. Remember, resonance is an amplification effect, and resonance is a special case of interference. So this is ultimately an interference phenomenon. Now, what makes a standing wave occur? All right, these are the criteria that are critical that I showed you on the PowerPoint. It's when you have first of all, you have to have at least 2 waves, and the 2 waves meet. And what's going to be true of the 2 waves? Well, they're going to be the same frequency. And you should recall that's a definite criteria of resonance. You have frequencies that are matching each other. But there's also other criteria in this case for a standing wave. If you recall, when we had the traveling wave going forward, then the bouncing wave, the reflected wave going back, they also had the same amplitude. Okay, so the idea is when the wave reflects off the boundary, it doesn't lose any of energy. And because of reflection, they got to be traveling in opposite directions. You can't get this effect if you've got all waves moving forward. Okay, so you got waves going forward, waves coming back at them, and if the timing is right, and that's critical, that's the frequency part, okay, then you will get zones where they're continually constructively interfering and zones where they're continually destructively interfering. So I'm going to give you a classic example. And we're going to eventually learn 3 different cases. So the first case and easiest one to understand is when you create standing waves on strings or slinkies. Okay, so I'm going to draw one such standing wave. It's going to look like this. So if I take a snapshot at one instant, it would look like this. Okay, and we're going to continue on with this, but what's labeled key points, right? So at any given instant, that spot right there at the end, the fixed end, is going to be a node. Right there in the middle is going to be a node, and at the other end is going to be a node. And then at the peak here, where I have the greatest displacement, the greatest amplitude, is an antinode, and then I have an opposite antinode there. And this, you don't have to know this right now, this is called the second harmonic. This is the second most complex standing wave I can get for a fixed string. Okay, now that's after a certain amount of time. After another quarter of a cycle, if you recall from the PowerPoint, the string is going to look like this. In other words, the whole thing is going to have 0 energy. And then a quarter cycle after that, it's going to look like this. So the antinodes flip positions. But the nodes are always at these 3 spots. Okay, so as we continue on, this part of the medium is always going to vibrate back and forth between these 2 extremes, as are these 2 parts. But right here in the middle and at the ends, they never are going to displace themselves. They're standing in place. And again, that makes it very different than a traveling wave. Okay, so node is a points of constant destructive interference, and an antinode are points of constant constructive interference. Okay. And something that's going to be important very later, that's very, very helpful in our analysis, is the distance between any node and its antinode, right? So from here to here, whereas an antinode, or from an antinode to a node, is always a quarter of a wavelength. Related to that, node to node is always a half a wavelength, or an antinode to an antinode. But generally look at differences in nodes. Okay, so in the chart here, I want to finish up just by summarizing the differences between standing waves, this special case of resonance, and normal traveling waves, the waves that we drew before where they look like this, and the pulses are continually moving in one direction as the medium oscillates perpendicular to that. Okay? In terms of energy, they both contain energy. That's what waves are about. But what makes standing waves different is they're not moving. Okay? The energy is not transmitted along the rope. It's basically stored in between the antinodes. And the antinodes aren't traveling forward. They're just going back and forth between two positions. Where in a traveling wave, the energy is continuously transmitted, let's just say forward. Okay, amplitude. We talked about that. In a standing wave, all points on the medium always are at a different amplitude. Okay, if I go back up to here, right, this point right here is always going to be somewhere between here and here. Whereas if I choose a point, let's say right there, it's always going to be a smaller amplitude. It can never achieve the same amplitude as the one to the left. Okay, and that's different than a traveling wave. So at the nodes, the amplitude is always 0. And generally at the antinodes, A max is twice the normal amplitude of the original wave that was being created. Okay. On a traveling wave, okay, all points will eventually have the same amplitude, just at different times. Okay, frequency. No difference. All points vibrate with the same frequency in both types of waves. So note, in the standing wave above, the frequency isn't changing. It depends on the source. All right, let's jump to wavelength. Okay, and this is going to be really important later on for analysis. The wavelength of the standing wave is based on the length of the string or the air column. We talked about brass instruments or woodwind instruments. Okay, so in this particular case, whoops, I just offset that. Oh well, we'll just have to live with that. This string, for whatever reason or for whatever choice, is a certain length L. So if I want to understand the wavelength of this standing wave, it's based on this L. In fact, I see this wavelength is exactly equal to L. If I had different standing waves that were fitting within this, so I'd say I had a standing wave that looked like that, okay, then the wavelength would be a fraction of L. So we'll see that you can alter the wavelength of the standing wave by altering the length of the air column or the string. Okay, so again, it might not seem obvious why that's a big deal, but it will become important later. So I apologize, this got all messed up. Just erase that. So it's based on that. And we're going to see, and I mentioned up there, okay, the wavelength is equal to twice the distance from one node to the next node. Earlier I said that the distance from node to node is always a half a wavelength, so a full wavelength would be twice that. And in a regular wave, a standing wave, okay, distance between any 2 points that are in phase with each other. Okay, in other words, that's just saying crest to crest or trough to trough. That's how you measure wavelength. It doesn't depend on the length of the slinky or the string that you're creating. Lastly, phase. Okay, in a standing wave, all points between nodes are always in phase. They're always moving in the same direction. They're always in the same part of the cycle. Whereas in another wave, a traveling wave, it looks like this. Every point along here is at a different part of the cycle, so they're in different phase. The big thing to summarize about standing waves is this is really important, and the energy consideration is important. Okay, so we'll do a lot more with this. This is one of the key things that the AP likes to test, so if you've got any questions, make sure you bring them to